We welcome your questions. You can submit them to us via email, questions@wll.com. And now, I'd like to introduce our presenter. Steve Ferguson of Compliance Direction, LLC, has over 40 years of experience in testing and device evaluation. He has instructed in the area of testing methods for the past 20 or so years, focusing on EMC, product safety, and environmental test methods. His comprehensive knowledge of MIL Standard 461, 810, 704, 1275, 1399, and CE marketing requirements for commercial and industrial equipment provides the ability to discuss the many aspects associated with regulatory compliance. With a background operating test laboratories and manufacturing companies, designing products, developing test procedures, and performing tests, he has the experience to address a wide variety of regulatory compliance topics. He presents various courses of EMI, EMC compliance, including EMC for nuclear power facilities, architecture shielding, and MIL Standard 461 testing presented online and at customer facilities. So, without further ado, let's turn our attention to MIL Standard 461 Calibration Verification with Steve Ferguson. Hi, Steve.
Well, good morning, all. How are you? Or good afternoon, or wherever you are. I lose track of what time of day it is. This afternoon in your location. So, thanks for that kind of introduction. Did you hand me the control ball so I can change slides?
Sure, give me one moment.
Okay. Well, as I said, welcome everyone. I appreciate you coming in today. About a month or so ago, we did a webinar where I joined in for a very short piece, and a question came up regarding calibration verifications and etc. So Mike invited me to present this element, and so here we go. This was solely based on a question that came up, so clearly we try to look at the questions that arise and deal with them. So I'll get my machine to work. There it goes. Why do we do the calibration verification? Well, the assurance that the measurement system works properly is one of the primary reasons. This is not just related to MIL Standard 461. Almost all EMC standards have a somewhat of a verification process just to make sure that what we're doing is in fact what we intended to do. And the systems are operating and the measurements we are receiving are somewhat validated, shall we say. And this is normally done in conjunction with the actual test. So the hardware that we've selected to do a particular test is checked out. And the software, that those control systems that are apply correction factors, things of that nature gets checked out to see that we are collecting the data properly. Now, as with any verification thing, the depth of how good it is depends on how well you've set up your procedures and your controls. But if we follow the steps and the various things that we'll be discussing, we tend to get a good level of verification. We also use the pre-cal or pre-test calibration work to check test levels and control limits for the susceptibility waveforms and test levels and etc. We normally check the waveform parameters and we set the drive level maximums or those that we'll be using for the test depending on which type test it is. As I said, we do this in conjunction with the test so that the standard reminds us that we need to look at the equipment we're going to be using. And the standard's pretty adamant about that. Apparently, people were checking some systems and using something else. So there's a continuous reminder in the standard to check the equipment. Also, Revision G came out in 2015, implemented a calibration change. And reading the statement, after the initial calibration, passive devices such as measurement antennas, current probes, and listens require no further form of calibration unless the device is repaired. Well, that came about to help reduce some of the costs of keeping instrumentation in calibration when there's very little chance that it was a problem. Items that are used once in a great while get put away and they're taken care of, and we pull them out and make sure that nothing's deteriorated through a physical inspection and things like that, and check these verifications to see that they're still working within their calibration levels. In other words, the correction and conversion factors are still applicable. So we're validating that. But the change did some processes that expanded what we're doing in the verification checks. We did some additional frequency checks and some additional tests that became necessary because the verification previously was pretty well limited. And the process for this thorough physical inspection remained with that revision. It's critical because spot checks do not cover all frequencies, and we are putting in spot checks. Some items are not present in the verification procedures. And as I indicated, there are some pitfalls present in using the verification solely. For instance, in the little graph that I've stuck in there, there's a couple of dropouts that you can see out around the 13, 15 gigahertz region. And that problem was related to a pinched cable, simply not detectable through the physical inspection. There's a slight pinch. Now, if we really pressed hard on the cable jacket and ran our fingers along the jacket, we could feel a little bit of a bump. But it took a fairly good, after we found the problem, check to determine where the pinch was or that what was wrong with the cable. So, and by the way, there's a little dot on the right side of that chart that's above the line, red line. Well, that's the spot check frequency. So these two dropouts would not have done that. I've wrote an article that included more discussion about that. It's available at my website and my blog area, the Passive Calibration. That links you over to Interference Technology that publishes it in their magazines and blogs. But things like connector spread, where a wrong connector got put together, like a 2.4 millimeter receptacle got pressed with an SMA type connector, where they screw together, but it also spreads the pin out. Shield terminations, where the coaxial cable doesn't get terminated all the way around. Loose fittings, corrosion, things like that come into being as potential risk areas, especially where a single or a few frequencies would get affected without affecting where we might be doing the element. That article kind of delves into some of those things that are beyond what that statement said. It includes other passive devices like cables and attenuators, things like that, and things that will come up. And also, there's a possibility of record keeping deteriorating, that we don't know when we last checked such and such probe, such and such cable. So we need to put into procedures when we adopt this verification check in lieu of calibration, then the record keeping should be used somehow to identify when we do these things. And just putting that we did the cal check in the report and without identifying onto the records for a particular probe or whatever, we don't have an easy way to find out when did we last know it was working good. So that's discussed in that article. With that, I want to go into the real purpose and talk about some of the various calibration verifications that we do. I'll go through several of these in a very top level fashion here. To go into depth on this thing, on details and etc., a longer training course would be appropriate if that's what you need to do. I do some training courses. You can check my website for availability. But the CE101 checks the probe, the cables, the receiver, the data collection software, etc. We configure it much like we see there and determine the voltage that's measured across the resistor that will produce the current limit minus 6 dB. We normally do these checks on for emissions about 6 dB below the limit to verify that we can see and measure accurately at that level, that we're not skirting the noise floor and causing a lot of ambiguity. So the test levels are created based on that. Adjust the signal generator until we get the voltage at the resistor. Now, that resistor, what do we do here? We select a resistor that will allow us with our generator amplifier to produce enough voltage so the current will flow in the loop from the generator through the resistor and back. And so typically a fairly low value resistor, 20-25 ohms, is not uncommon here. So we can produce the current without having to drive such a high voltage. And we calibrate the details of getting the resistor value. Execute the software, apply the correction factors, confirm the measurements and tolerance. I throw a question in here that we'd like to see. Is the oscilloscope set for high impedance or 50 ohm termination? Well, if I do a 50 ohm termination, the resistor is in parallel with the oscilloscope 50. So if I'd selected a 25 ohm resistor and a 50 ohm oscilloscope, we have about 16, 17 ohms of resistance. And so the R value has changed. So we want the oscilloscope not to affect the measurement. That is a measurement instrument that should not have the effects. We need to select 50 ohms if our measurement device demands 50 ohms for its calibration. Like the current probe output going to the receiver is a 50 ohm termination, and the correction factors have that necessity to make it 50. But adding this oscilloscope, if I use a high impedance, the R value isn't affected significantly. So I now can calculate what the the voltage is at the known resistor value. It's possible to do it to 50, but normally we want to select the impedance matching to do what we need to do. We do not want to put a couple of things in parallel to affect our numbers. CE102 has a similar kind of arrangement, except we're going to be checking voltage for the listens, the cable, the attenuators, the receivers, the data collection software, much like anything else. And when I configure it as I show in the diagram there, after we get through the two low frequencies shown on the diagram, 10.5 kilohertz and 100 kilohertz, we would get rid of that T in the oscilloscope for the higher frequency checks. We determine the voltage, minus 6 dB, adjust the generator, execute the software, apply the factors, etc., confirm we're in tolerance. And then we need to do a second piece. This was added for 461G because we weren't checking the impedance of the listen. The listen impedance at 10.5 kilohertz is somewhere approximately about 5 ohms or so. So the signal generator output is a 50 ohm source. So when we attach it to a 5 ohm load, it loads the circuit down. It loads the output of the signal generator. So even though it says we're outputting some voltage, what we're actually outputting is reduced significantly because of the loading effects. So the oscilloscope is used to measure what the voltage really is. Now this unloaded loaded test of the signal measurements to verify the impedance. If I was to set these up and get my test levels with the oscilloscope being the measurement point, and I disconnect the 5 ohm termination. In other words, the listen that comes away from that cable. And the signal generator is no longer loaded by 50 ohms. It's an open circuit out there. So the oscilloscope voltage will rise dramatically because the loading effects are gone. So we measure what the oscilloscope voltage is and determine how much it changed from the loaded measurement where the listen was connected. And for 10.5 kilohertz, we should elevate about 14 dB. So the ratio is about 14 dB. If that is in fact valid, then it indicates that our impedance of our listen is in fact correct. It's within our tolerance range. So that's the part B step that got added for the 461G. And why do we put that attenuator there anyway? The listen attenuates power frequencies. Well, when we first start up and apply a high voltage like 120 volts, 240 volts, or etc., there's an inrush of current through the listen coupling capacitor that gets terminated by the measurement receiver. And that high level of current, because of the short circuit action of the capacitor, damages the receiver. So we put the attenuator in to prevent that overload. Now, sometimes to get sensitivity, there's a need to reduce how much attenuator. The standard shows about 20 dB. A lot of people use transient limiters in place of the attenuator, or a way to get the attenuator out of the circuit if a greater sensitivity of the measurement system is demanded. But we need to be cautious because that initial check is going to be damaging to our receivers. So be cautious in applying without having some kind of attenuation going on. CS106 gets a little complicated for those of you that deal with radio receivers and transmitters. The receiver function is pretty straightforward because in the test we connect directly to the antenna port instead of having an antenna radiate. So this system checks the cables, attenuators, couplers, rejection networks, amplifiers, receivers, and our software. So in our transmit mode, like is shown in the sketch here, we would have a lot of attenuation, especially depending on how much power our transmitter is, 100 watts, 1,000 watts, etc. We may need to heavily attenuate the signal to prevent damage. We also need to reject the transmitted signal. We need to have that rejection network lower the level so we can get sensitivity. If I've got several watts of power coming through here, then a rejection network needs to prevent the overloading of the receiver, driving it nonlinear. Because if we just put straight attenuators in, we lower the amplitude of the unintended signals in conjunction with controlling the transmit level. We may need to connect at several places where we inject the signal to check all the systems. The attenuator and coupler together may be too much attenuation to allow a signal generator to overcome the losses. So we may need to check the attenuator and then check the coupler and check the rejection networks, etc., and then stream them together to get our overall element. We also have multiple connection points may be tested. There's always a risk that when we disconnect the junction here to check it out and we reconnect, that we don't get the termination or the connector set right. So we have to use some caution when we do that. Just like everything else, we test to the limit, 6 dB below the limit, and adjust the generator to make sure it measures correctly. I get through another question here. Why is the dummy load necessary? The directional coupler needs to have current flowing through its straight through port in order to couple properly to the side arm or the measurement port, the forward power port. So without having a dummy load directional coupler, calibration is thrown off. We do need to dummy load it with the expected impedance. So a straight through connection on the coupler will take care of doing that. Okay. RE101 comes into being here where we're using a loop antenna that's fixed. It's a passive antenna. So when we configure for the test in the part A, the upper part of the diagram, we remove the antenna and put a signal generator into the cable that would normally be connected. We determine the voltage to be applied minus 6 dB minus the antenna factor at a single frequency for checking 50 kilohertz. Now we had to take away the antenna factor and the 6 dB because the antenna is not physically present. But the measurement receiver thinks it is because we say we're using that antenna. So the software is going to apply those antenna correction factors or conversion factors. So we need to have that signal low enough to allow that to be added and still measure at the 6 dB below the limit point. Adjust the signal generator, make sure everything is working right, apply the factors, confirm the measurements are correct, and then we do part B of the check where we put an ohmmeter between the connector center pin and the outer conductor, and it should get 5 to 10 ohms. That's a pretty wide range here. I usually like to collect this thing when the antenna comes in and say it's 8 ohms, for instance, and then when it starts deviating from 8, I get concerned that there's something going on inside the loop where the wiring insulation may become frayed, or we use this loop antenna to do a susceptibility pinpoint and overheated the wiring, insulation meltdown, things like that come into being. So the check is kind of significant. And keeping records of what we got. That's why I look at putting a record on that antenna records to say on date X we did the sanity check and it was 8.3 ohms. And then the next time it's done, we record it and say on this date it was checked and it was 8.2 ohms, or whatever. But if we see it going away or becoming more radical, then we need to keep up with that and look at saying there's something going on with the antenna. RE102 verification does a similar thing where we check the cables and etc., the software. Plus, there's a stub radiator performance check. We set it up just like we would for the RE101 where we connect the cable in place of the antenna, set the limits, and remember the antenna factor has got to be subtracted from our test voltage because the software is going to add it back. We collect the measurements and see after we apply the factors that everything is in order. The stub radiator is like a coaxial cable that radiates a signal at a frequency we set. Now, this relationship of the stub radiator to the received measurement is a kind of a random event. The standard says use it for an appropriate signal. Well, how close to is appropriate? If we set the stub radiator in one place every time in relationship to the antenna, then we should get similar answers over and over again. And having that information says that little things about our antenna like corrosion or a fitting problem or something, even though we may get a signal, it may not be a correct value. So setting a stub radiator in a fixed location and the antenna, we can get the same answers over and over again, much like we need to do for a test where this validation is set up in a standard. In the commercial world, it's done that way to where you set your antenna and you always need to get the same answers. Now, the rod antenna comes into being here is a little bit more difficult or different. So in that case, we would take away the rod and hook up a 10 picofarad coupling network into where the rod antenna goes. And we would inject the signal across the 50 ohm termination to develop a voltage for the high impedance rod input. And that measurement should be present. The 6 dB termination allows the signal generator to have current flow and develop a voltage that's needs to have a correction of 6 dB, plus the rod is missing, so there's another 5 dB factor associated with that. These correction factors are present. So the rod antenna, by the way, be cautious with the rod antenna. When removing it, it's very sensitive to ESD events. The input circuitry is a high impedance and really sensitive to the ESD. So you need to be cautious about discharging yourself when you're connecting or disconnecting the rod. CS101, we'll go into susceptibility a little bit. The pretest calibration establishes the maximum required power to be applied, and it also verifies linearity of the equipment. The limit is based on power dissipated by a half-ohm load. Now, we see in the diagram that I've got a signal generator into a power amplifier driving the coupling transformer, and we produce a power amplifier output that will get at the low frequency range to dissipate 80 watts is the power limit. We can get to about 6.32 volts or so, and we adjust that. We measure the power amplifier output with a voltmeter. Having the measurement with the voltmeter at that point allows us to be able to adjust the amplifier gain and have the voltage proper. If I measure at the signal generator output, I'm not allowed to vary the gain of the amplifier without a recal. So if I come to higher frequencies where I might need to read the gain of the amplifier to get a signal out of noise, then we need to compensate for having that measurement. So I typically use the voltmeter located at that point. Other folks have hooked up automated systems where they control the voltage at the signal generator output. Now, sometimes they'll do this without providing feedback. So if I do this during the calibration and the test is a low impedance circuit, I can overdrive heavily because the signal generator will push a lot of voltage or will push a lot of current. So the idea is to current limit. There's a paper that I've written or co-authored discussing that. That's available at the Interference Technology website or on my blog also, if you want to read more about things that we may be seeing change to compensate for that. The different power amplifiers in use around the world get different answers if we use the voltmeter output versus the signal generator output. There's a significant difference, and the difference is more pronounced depending on what amplifier is in use. Anyway, we record the settings so we know what the maximum power is. CS114 has a similar type arrangement with the maximum current to be applied, and the monitor probe verification is done here. In the part A of that diagram, we inject a signal into the injection probe through the directional coupler and use the directional coupler port to measure the forward power. So we've got a reference point so we can record that to play it back. We go into the circuit where there's a coaxial load and a measurement receiver. There's also a monitor probe stuck into this path that's just set up to a coaxial load or dummy load, whatever you want to call it. Now, that checks our settings, our power levels that produce the calibration current. Calibration current is a current that's different from the test current, and some of that is related to the fact that the coaxial load and measurement receiver puts a 100 ohm circuit or current loop things into 100 ohms. So when test comes about, we always test 6 dB higher to simulate the 50 ohm cable. And we test at 6 dB higher than the most current limit that we would have. That's a minimum. We also bring into being section B of this calibration, where now we move the measurement receiver to the monitoring probe. We play back the signal generators things that we did during part A of the calibration, and we measure the current to see that it follows the calibration current limit line that we use to generate or get our maximum levels. Now, this is a checking of the monitoring probe. The concept was that it's a more thorough all frequency type calibration check. So this was added to 461G because the passive devices exemption clause. So this is a much more thorough area. By the way, I consider CS114 to be one of the more error-prone tests. People don't necessarily understand that this is a conducted test simulating a radiated event. So we need to be very careful when doing this. Also, a lot of parasitics, cable placements, things like that start affecting the answers quite a bit. It can be a significant impact. So look at CS114 and how you do it. I've seen it done incorrectly more often than I'd like to imagine. CS115 is a similar kind of thing, except it's an impulse signal. And in this case, it's much like the CS114, except we drive a pulse generator into the injection probe. Note that we're not calibrating our pulse generator. We're not calibrating the monitoring probe that will be used during the test. So we assume that the monitoring probe has some sort of a check. Now, we're going to use a probe here that's got a frequency range that's very high, up maybe 500 megahertz. For CS114, we used a top frequency of 200 megahertz. So are we really getting the probe checked, or are we using a different monitoring probe during this test? And there's no checking of it during the CS115 verification. So we need to be aware of that. We use a time-based oscilloscope instead of a receiver, and we generate waveforms depending on the iron content of the probe. We may get a waveform like on the left of that diagram, and a different, more nickel related core could give us the waveforms on the right. So but either ones are acceptable. We need to verify our transition times. Remember that the monitoring probe during test will be there, and the correction factor for this waveform is based on a 2 nanosecond transition time. So we would select 175 megahertz as the monitoring probe correction factor. 175 gets us that relationship of what a sine wave would need to be to create transition times when we integrate all of these various signals to make the impulse with 2 nanoseconds. CS116 is a similar kind of function here with a dampened sine generator. And we use a time domain oscilloscope thing. We verify the waveforms and adjust it to the peak. By the way, go back to 115 for just a moment. The settings that we collect during that calibration of the waveform, those settings are used to drive the test. We're not using it as a maximum, we're actually setting. So the test could see more or less current than we got through our calibration. So, but it's the standard tells us to do it that way. For CS116, we do a similar thing, except now we're going to verify the maximum to be applied. So we measure the applied current. If we get to the current before we get to the maximum setting, then that's what we use. If we go to the maximum setting, we record what current was produced. We need to verify the frequency in the dampening, or the Q. The Q is how quickly the waveform dampens or goes from a peak current to the midway point. And that relationship, using the formula that's in the standard, should be 15 plus or minus 5. So our generator into this calibration jig validates that Q. If the Q is very short, in other words, we don't get much ringing at all, we tend to have an impedance mismatch. If we get ringing, it goes on forever, a different form of impedance mismatch, or a low impedance because it dampens quickly, or a high impedance because we fail to dampen. We check it at the various frequencies that are assigned for the test, which are 6 standard frequencies, plus the standard talks for using a resonant frequency. Most of the time, we have no idea what that is. We can't control every installation to determine the resonance of the circuit when it's installed. So duplicating that is something that's not realistic. It's a waste of energy because we could check a particular resonance because that's what the room setup did, and the installation is no place close to that. So it's not providing any information, but it provides a lot of work. CS117 is a transient event that came into being with 461G. And again, just like everything else, we're checking the waveforms. And we set up the test levels and limit levels. These waveforms that we have a test voltage waveform will have an associated current limit waveform. And a current test waveform will have an associated voltage limit waveform. Voltage limits are verified with an open loop circuit there we see in the diagram, and current waveforms are shorted loop. So in other words, we put up a extremely low resistance for the waveforms. And we establish these things as the capability of our transient generator to produce and create enough test level. These are pretty stringent waveforms, and this test is not done at a lot of labs. They don't have the multi-burst, multi-strike simulation equipment. Pretty expensive to get into this business. So unless there's a lot of demand, we don't do that. During the test, the generator verification settings defer to the measured voltage or current. The verification demonstrates capability. So if we don't attain the voltage or the current, our limit level could come into being, and this verification makes sure that we validated we can achieve the limit waveforms, and the test verifies that we can get to the test waveforms, which one or the other. CS118 or the ESD verifies the waveform and the ability to attain the test level. The top part, the tip voltage verification, is simply a air tip that's charged up. We bring it into the range for the electrostatic voltmeter to measure the voltage appearing on the tip. It should be what the dial on the generator says. Then we apply the discharge current waveform as a conducted waveform into a target. The target parameters are established through IEC 61004-2. The mill standard uses the equivalent target for that for the human body model for personnel born. Now, by the way, these waveforms do not appear as the same as munitions ESD test, or mill standard 331 or JOTP 062. Yep, 062 is used for the ordnance waveforms. There's a different human body model. And the target is also different for those standards. So we need to verify the waveform at the various currents that are doing a direct or contact discharge. And we see that the waveform follows the shape that we have over there with some measurement points for the current to say that's what we have at those points. The standard is pretty specific on doing that. RS101 field verification. This checks the relationship between the current flowing in the radiating loop and the field being measured by the monitoring loop. These things are built into each other, as we see on the left diagram. The monitoring loop and the radiating loop are standard equipment base built with these parameters to the government spec. We calculate the current necessary to produce the flux density. Flux density in an air media is 9.5 E7 picotesla per ampere. So the idea is 950 nanotesla. So we configure it as shown, adjust the signal source till we get to the current necessary to produce that field at a frequency of 1 kilohertz. We measure, after we got the current flowing in the loop, we measure the field at the field monitoring loop to confirm that our calculated current to flux density relationship really exists for those parameters. And that 9.5 E7 is the parameter for that standard loop configuration. After that, we use this relationship to determine how much current we apply through the test frequency range. Now, some people, instead of putting a current probe to measure the current flowing in the loop, they put a low value resistor and measure the voltage. Anyway, you're trying to get a known value of current flowing through the loop to produce the test levels. So some of these test methods were omitted. They use active measurements during the test, or it's so seldom done that we don't necessarily get a lot of information in the pre-cal. For example, RS103 could use pre-test calibration. In other words, you set it up and calibrate the field where the UT will sit, and then you play it back once we set up the UT and operate. Sometimes we simply use active measurements of the field during the test as a more common method. Waveform verifications don't resemble the applied test waveform. Circuit characteristics, parasitic elements, etc., cable placements, coupling, all kinds of things that distort the waveforms. So when we measure the test waveform, it won't have the same appearance as our calibrations. In many cases, the verification has been expanded just to verify these passive devices that have been exempted from the periodic calibration. This verification process applies to the configuration each time it's done. Record keeping helps track when we did the last things. Now, for instance, that cable pinch I talked about earlier, that cable, if it was used between the signal generator and the power amplifier for RS101 testing, I may not have ever noted that that cable was bad, because the software will overcome the losses of the cable and give me the field strength necessary, so I won't recognize that I've increased my drive level by 20 or 30 dB. I just simply have overcome it if I've got that much range. But put that same cable on the output of the amplifier, and the losses would cause us to have to saturate the input to the amplifier. So depending on where it's located, and we do these things with the cables used in the susceptibility test, and when we bring it over and put it in an emissions test and it shows up bad. Well, how many susceptibility tests have the flaws going on? So keeping records is an important aspect. The standard reminds us to use the test verified. Users must have created this reminder need by checking some instruments and using something different. This verification process is a necessary function, but as I've indicated, some pitfalls exist. Establish lab procedures to mitigate gaps into that. That article I mentioned for passive device calibration could be beneficial in doing that. You can reach me at stevef@compliancedirection.com, and I'm open for questions. Kim, I'm going to let you host it and ask me any questions that came in.
All righty, we got a few questions actually. So let's get started. Does one float the oscilloscope for CE101 testing calibration?
Could you repeat that again?
Sure, hope I'm reading that right. Does one float the oscilloscope for CE101 testing calibration?
I see, float. In other words, put an isolation transformer on. It's not necessary here because of this CE101 is disconnected from the ground. CS101 would put the isolation in the oscilloscope because we measure with the ground of the oscilloscope connected to the neutral lead. In some applications, the neutral lead is not grounded, and that can cause a sudden ground element, and there's a flame about 10 centimeters to 15 centimeters tall when the oscilloscope probe burns up, if I allow that to happen on a 240 or a 483 phase circuit. So we do not need to float it for the CE101. Good question.
All right, next question. If we can talk a little bit more or address the importance of the attenuation in front of measurement receivers when starting tests as in conducted emission testing?
I believe that was in the CE102 area where that attenuator shows up. As the current, when the voltage is being applied to the UT through the LISN, the voltage shows up on the output of the LISN or the EUT side of the LISN, where there is a coupling capacitor located. That coupling capacitor, when voltage is first applied, tends to take on a charge very rapidly or acts almost like a short circuit for that few microseconds. And that short circuit pulls current through the measurement receiver that terminates that coupling capacitor. When that current is high like that, the 50 ohm termination of the measurement system sees that high current and the attenuator goes up in smoke. Once we let the smoke out of the attenuator, that's not functioning anymore. And that's the measurement attenuator of the oscilloscope, not an external attenuator. So we put a high attenuator in line with that so it can limit how much current flows when that capacitor initially sees the charge change. So that rapid change is now taken care of, and we're controlling how much current flows. So we see a high level of attenuation. What comes through the measurement receiver is no longer such a high current, and we reduce our potential to damage. I hope that gave enough more information.
All right, thank you. The next question is CE102 verification. Do we need to terminate the measuring port of LISN and other line with 50 OHMS?
Well, you're only checking one LISN at a time. When I'm doing the test, the multiple LISNs come into being, one for each phase lead or neutral lead. And now they need to be equally balanced because now we're tying it to the UT. So balancing it with the terminators and having the one we're actually measuring terminated by the receiver puts a balanced circuit into all leads simultaneously. So during calibration, you only have the one LISN involved at any time. So the termination is done by the oscilloscope, by the measurement receiver. Okay?
All right, next question. They said on slide 7, is the use of a spectrum analyzer okay instead of a selective measurement receiver?
Let me see if I can go to slide 7. Help me get there. There's 7. Now repeat again with the question.
Sure. Is the use of a spectrum analyzer okay instead of a selective measurement receiver?
Most laboratories use spectrum analyzers as an alternative to the receiver. The receiver provides us a little bit better sensitivity and more ranges. It also allows us, especially in the current receivers that have a lot of bandwidth, they also do the fast Fourier transform, and etc. Those are allowed to be used. So it's a little bit more common today to see the use of a measurement receiver. However, spectrum analyzers have been used for quite a bit. Now, the difference being their sensitivity, dynamic range, and etc. However, also some spectrum analyzers do not have what's called an EMI measurement mode. So the bandwidth of that spectrum analyzer is based on a 3 dB calibration, and the measurement receiver is based on a 6 dB bandwidth. So the idea is that we start limiting the bandwidth on the spectrum analyzer. And in fact, what we don't do is we expand the bandwidth, because the 6 dB points is about 1.8 times the selected 3 dB bandwidth. Let me translate that just a little bit. If I selected 10 kilohertz bandwidth on a 3 dB spectrum analyzer, the measurement bandwidth for 6 dB would be approximately 18 kilohertz. So now what we've done is we've allowed more energy to come through for broadband signals. That's a function. I really get into depth with that during the lengthy training classes I do on 461, because we talk about what the effects are and the fact that the standard says we can't compensate for it. And I talk about the whys we can't, and et cetera, and show you what's going on a little bit through the diagrams. But that's like a 4-day course. So, but it goes much more depth into this particular area. Okay.
All right. But what if the power amplifier impedance is much less than 0.5 OHM? Then a lot of extra current might be injected into an EUT.
I'm sure you were talking about CS101 here. Yeah, CS101. That's common. That power amplifier impedance, what we sometimes do is select a 2 ohm output. The coupling transformer slated for this test has a 2 ohm primary, half ohm secondary. This transformer is built by the government print, so it comes up with those parameters. So the power amplifier impedance is very low, usually 2 ohms or less. Now, it doesn't say that we can't use something else, but what typically happens is we start overloading and causing distortion of the amplifier. Part of the calibration checks here are to verify that the waveform stays linear, stays sinusoidal. The sinusoidal waveform would indicate that we have limited distortion of our power amplifier, or we're maintaining the operation of the amplifier in its linear region. So we're operating it within its specified boundary conditions. A lot of different amplifiers are used throughout the world, so we need to be cautious of that. We've encountered several problems where audio frequency amplifiers are used with a lot of power, but their dynamic range or frequency range gets to be limited. They're good up to 20, 30 kilohertz maybe, and then they start not being very good at the 100 kilohertz region. So our attenuation or operation of the amplifier becomes highly distorted. So we have to be cautious in our calibration to see that throughout the frequency range we maintain a good linear operation of the power amp. Hopefully that answered.
All right, thank you. Next question. How does one handle failures when they occur?
How does one handle failures when they occur?
Yes.
Well, our target here was to discuss the calibrations here, and failures in the calibration area is the fact is it's identifying flaws or problems with our test and measurement equipment. Something's wrong. So we need to start replacing, adjusting, verifying, and et cetera during the calibration checks to see what is causing it. For instance, a current probe calibration might show up as being off, okay? And what could be wrong with that? Well, the probe could have been dropped and we don't see physical damage, but the core could be cracked and causing a change of operation here. That current probe calibration could also be the fact that we, in our software, are saying we're using probe number 1 and its factors. And in fact, what we connected was probe number 2, and we didn't have the right factors in our measurement system to make the proper corrections. So the cables could have a problem with them. We could have a long cable installed on the current probe because we want to reach a long distance here, and we see a reflected waveform from the cable length. We forgot to get rid of that T connector, and we see a standing wave problem on the cable when it's fairly long. At these frequencies for CL102, it would take a fairly long cable to cause that event, but I've seen it happen where the T connector wasn't removed at the higher frequency calibrations, and the T and the cable that was attached over to the oscilloscope was a little bit long, and got a standing wave issue with high SWR. So many things could be there, but that's what we have to do to figure out what's wrong with this, make the corrections, and then redo the calibrations. If we identify that the impedance of the listen is in fact wrong, we'd need to get that listen repaired. Probably a burned out resistor on the primary side is a common occurrence in a listen. So lots of things can go wrong, but these checks tell us we may need to have a repair on the passive device. Okay.
Okay, thank you. What about the attenuator uncertainty?
Attenuator uncertainties. Mill Standard 461 doesn't require uncertainty calculations. It doesn't say that it doesn't exist. It just says that we should be correct. Okay. Now, are we correct? What is the uncertainty allowed to be? And typically the international standards, the commercial world, gives us an uncertainty budget. Or for instance, for an open area test site, we have a 6 dB uncertainty budget for doing radiated emissions work, according to the IEC standards, the CE standards, the ENs, and things like that. So it says that our measurements need to be within 6 dB of what's absolutely correct. That seems like a lot, but there's so many factors on an open area test site that affect the budget that we need to be considerate of that. And these uncertainty things could certainly come into being. Mill Standard 461 says that they don't require or identify an uncertainty budget. I think that may be a gap in what they want to have happen, but it's still allowed. They assume that the limits that they've created allows for a normal uncertainty without defining what normal is. So it's a little bit ambiguous, but using the international standards for uncertainty budgets certainly gets you within a good accreditation scope for getting your laboratory to say I'm doing the right thing. Okay.
Question, bear with me, it's a little lengthy. So, in the CS116 test, unlike the calibration, the signal waveform injected into the EUT is sometimes distorted significantly during the test due to the EUT impedance, especially at 30 and 100 megahertz. How can we measure and limit the actual injected current by using this distorted wave shift? Also, does the max peak of the disturbed signal on the scope screen really give the peak of the actual injected damp signal by using the CW probe factor at the frequency of interest?
Well, Kim, I hate to do that because it's a fairly lengthy question, but I want you to break it down a little bit.
Sure. So I try to read it how it's
in parts.
Yeah. Okay. So the beginning. In the CS116 test, unlike the calibration, the signal waveform injected into the EUT is sometimes distorted significantly.
Okay, let's stop there.
Okay.
That waveform, as I indicated, once we go into the circuitry, parasitic elements start taking over. How much capacitance between the cable under test and the ground plane, how much cable to cable coupling we get. And these parasitic elements really affect the waveforms, and they become more prevalent at the higher frequencies. So there's not much you can do about it because that's the realistic circuitry. Remember, 461 does tell us how they want the cables arranged. 2 centimeters of space between cables that are in the same plane, 5 centimeters elevated, the length is, etc. So the idea is that the waveform distortion is allowed in the test area. That validation of the waveform is done in our calibration jigs where we control those parasitic elements. Okay, now we can take the rest of it.
Okay, second part is, how can we measure and limit the actual injected current by using this distorted wave shape?
But remember, the waveforms are measuring the peak current. So you go to the highest peak for the measurement and whatever that is, and you're going to get a little bit of variance. It's going to shift a little bit from sample to sample. So you need to take the nominal event of that particular waveform. This is kind of significant to do and capturing that peak and recording it. It also tells you what the peak current was, so you can determine were you driving the maximum setting or were you attaining the target current. So those measurements are necessary, along with a waveform recording of what the waveform looked like. Okay, each cable should have its waveforms recorded and put into the report at each one of the test frequencies. Okay. Any more of that question?
No, I think that's pretty much it. But before we continue, I just want to let you know it's 2 o'clock. We have a handful of questions. I just want to respect your time. Are you still open to answer a couple more questions?
I'm sorry, Kim, I missed that.
Sure. I was just wanting to check in with you and let you know we have a handful more questions, and I'm okay with reading them. I just wanted to make sure you are okay with answering them.
Go for it if you're willing to stay online.
Okay, let's go for it. The next question, and thank you for that, is also a lengthy question, so I'm going to try to break it down as I read it. For calibrating the 100 kilohertz signal, when I inject the output power of the signal generator set to -6 dB of the limit, which is converted to -39.1 dBm or 2, bear with me, MVRMS, to the power output of the listen, the oscope measures the signal at 24 MVRMS. The question is, should I be calibrating the signal before connecting to the power output of the listen?
You establish the measurement using the oscilloscope, and that's the CE101, I believe we're talking about. Excuse me, CE102. The 100 kilohertz, you would inject the signal into the listen with it connected and adjust the voltage using the oscilloscope measurements. Okay? And in doing that, you allow the signal to be loaded. Now at 100 kilohertz, the impedance is 20 some, almost 30 ohms or so. So we load it somewhat for the 50 ohm generator. When I disconnect the listen, the voltage goes up, and that's where you get your millivolts measurement. We convert those into a decibel equivalent to show that the ratio of one to the other was a 3 dB function. So I believe it's 3 dB for the 100 kilohertz signal. So the signal amplitude measured on the oscilloscope would go up. Now, this gets to be a little bit math intensive. So what I do is during the long training courses I do regarding this, I use a spreadsheet that has the calculations already there. All you have to do is modify the sheet to put in your particular probe, your particular listen, your particular, etc. And then it does the calculations for you and checks the ratio. Now, I don't send those spreadsheets out except for people that attend the course because they need to learn how to use them. They're fairly intensive spreadsheets. So just being aware that you get the right answers. It's just a cumbersome math issue. So having a good spreadsheet for emissions really helps with that. Okay? Hopefully that took care of that.
All right, 1 second.
By the way, I noticed a question regarding my statement about the open area test site uncertainty. And I see a couple of people have already put in some answers to that. I did want to point out that the 6dB budget is the normal budget with the normalized site attenuation of 4 dB. Normalized site attenuation is a part of the overall budget. So that's the big element in the 6 dB uncertainty. So just to add to the people that have already kind of answered that. Okay.
All right. Hi, Steve. It's Christina here. Just going to kind of go through some more questions with you. So what is the position and orientation for field monitoring loop in relative, and I guess relative to the radiating loop? Let me ask that again. What is the position and orientation for field monitoring loop relative to the radiating loop?
Okay. I want to go to that slide. Bear with me for just a moment. This is a particular slide. The field monitoring loop, and I don't know if you can see my mouse moving, but on the left-hand side picture where we show the probe, we'll see that the field monitoring loop is that little black circle beside the white radiating loop. And on the side view of that probe, you'll see that the red band is the coils for the radiation, and the field monitoring loop is placed on the right side of that with a little insert into the Teflon base. So that positions these things according to each other to get that 9.5 E7 picotesla per ampere relationship. Okay, so positioning is fixed by that. Even the screw to hold that together is a nylon screw, so metals aren't affecting the field flux density lines. So there's your positioning relationship built right onto the probe. Okay. Okay. Any other questions?
Yeah. This person also asked if the lab procedures, are they acceptable or traceable to any relevant standards, and how to ensure repeatability among the different labs?
Well, the accreditation bodies for various type systems validate that. That's part of when you have your lab accreditation. They do the checks to see that you are in fact doing things by the standard. Now, how much lab uncertainty between labs? Well, I remember at Washington Labs, we encountered this one time where another lab had done a very similar test. And when we compared the results, the two labs were within 2 dB of each other across the frequency spectrum. Our worst case differences were 2 dB. You can also participate in round robin checks to see that they send a test article out in every lab measurements, and you can see how your lab and your people compare with other measurement people. So there's lots of integrity ways to validate you're in fact going with the standard and the expected results. Okay.
All right. Let's see. For RS-103, is it mandatory to use a field sensor near the EUT to adjust or control the E field during EUT exposure?
Not mandatory. You could, in fact, pre-calibrate your room and use an antenna or probe just to see that something's there. So an antenna in place there, having something that says I'm operating, that I am in fact radiating at a reasonable level. And the calibrations could be pre-done. No standard calls for pre-calibrating with the EUT not there to get a field thing. If you want to use a reverberation chamber for RS-103, you'd have to pre-calibrate the room and then place the test article in with a sensor somewhere to see that you are in fact radiating, but we're not controlling it based on that. It was a preset drive level, We're just simply monitoring the fact that it's functioning. Okay.
Okay. We got about, oh gosh, 5 more questions, if that's okay.
Well, we'll go. I'll go to 1:30
All right, great.
or 2:30 your time.
Okay, sounds good. All right, next up, what is the general formal requirement for calibration of the test equipment? Do we have to use the services of an external accredited ISO 17025?
Well, that depends on your accreditation. How much do you want to do that? If you want an accredited body to endorse you, you're going to have traceable calibrations, traceable to NIST or ISO 100, 10012. And they call out several things like SAE 948 for antenna methods and various and sundry things. But bottom line is it needs to come back to in the U.S. to NIST traceable, National Institutes of Standards and Technology, and or the ISO 10012 for the international approvals. So you need to somehow get to that level of calibrations. Now, could you operate your own lab where you do nothing but pre-test? Then it's a matter of how much you want to allow. If you always go to an accredited lab for the formal elements, can a user accept something? They can accept whatever. Like for international CE marking, you declare that you comply. It's a declaration of conformity. People do that based on an analysis instead of test. Now they're taking a risk, and the accreditation people like to look at it to say, where's your background? Where's the test report? What's the accreditation of the lab? Did they know what they were doing? Did they get it right? Things like that always come into being here. And if you're showing up a problem and you're in an international CE mark, you declared conformity, you have no evidence of any validation, etc., and the test samples from the marketplace say you're not compliant, you get barred from selling. Your business goes, you can get legal penalties, fines, jail time even. So that's falsifying the records. So there's a lot of things that tell you want to get a reputable calibration thing that is traceable.
All right. So here's a question for CE 101. Use a differential voltage probe instead of floating the oscilloscope. Sounds more like a comment. I guess we're looking for
CS101?
CE 101, actually.
CE? I don't see how a differential probe got a differential probe because I'm not measuring between things. Now, that's a current monitoring probe. That wouldn't be a differential probe. CS101 could use a differential measurement instead of the standard voltmeter, but I don't think CE101 would be. I haven't thought about it very much, but it doesn't outwardly appearing. I don't think that's the right thing to do.
All right. Well, let's see. Another one. It says open area test site uncertainty under CISPR is rather plus or minus 4 dB.
Right. I mentioned that a couple of minutes ago. That was the normalized site attenuation. That wasn't a complete uncertainty when using a open area test site. 6 dB budget is by the international standards for the open area test site. And the normalized site attenuation, the 4 dB function, becomes an element of the uncertainty to drive that high for 6 dB total uncertainty.
Okay, yeah, and yeah, someone had actually commented the same, saying it's a qualification. Uncertainty budget is described in CISPR 16-4-2.
Yeah.
So it looks like I got one more thing here. Ooh, maybe it's another comment. It says the overall measurement uncertainty in commercial CISPR and CC64 radiated emissions is on the order of 6 dB K is equal to 2, 95% confidence interval.
Yep.
Well, okay.
I agree. That was a validation of that other comment, I believe.
Okay, yeah. Let me see if we have any other questions. I think we've pretty much gone through everything. So unless you have something else to add, I guess we can go ahead and button up here.
Okay. I appreciate the invitation to do this today, and hopefully we have a lot of things. I'm available for comment. You saw my information outreach to me. If anybody wants to do that, they're welcome.
All righty. Well, thank you, Mr. Steve Ferguson. It's been fun going through things, and I'm going to go ahead and end the meeting now.
Okay.
All righty. Thanks, everyone. On behalf of Washington Laboratories, everyone have a great day and stay safe out there. Take care.